All right, let's go through some virtual lab data, huh? So the name of the hydrate that I chose was copper sulfate. I'm going to write it like this. I'm going to write it like, I get that it says the name, but I'm going to write copper sulfate dot question mark waters. And that's the whole purpose of this lab, is to figure out how much water was embedded amongst the copper sulfate crystals. We had the mass of our evaporating dish when it was empty. That was 52.39 grams. The mass of the hydrate, I used a little extra, 1.69 grams. It's totally fine. Then we heated the hydrate in the dish. Afterwards, we had the mass of the evaporating dish plus the anhydrous salt. That's the salt without the water. And that was 53.41 grams. As far as observations go, maybe we would say something about there being a color change. We could say the color changed from kind of a light blue to white. Now, sometimes we'll notice like some chunks in the evaporating dish that don't heat evenly, so you might see some speckles of blue. Sometimes you might see it turn a little brown around the edges if we overheat. Sometimes you might see a little splattering if you're heating a little too aggressively, whereas some of the blue solid kind of like pops out of the evaporating dish. I didn't see too much of that, but it could happen. All right, so we've got our data, and when you're writing this on a piece of notebook paper, scratch paper, all you have to do in the data section is make sure that you've obviously got the numbers recorded properly. Measurements would be done with proper sig figs, although here we're just measuring things on electronic balances. And you would put units behind all of your numbers. There, that's the data. Now I move on to the analysis. And so on your paper, it's totally fine if you just want to write like number 1, number 2. And if you want to kind of label it mass of the salt, mass of the water, that's totally fine as well. And in the end, you're just going to upload photos of your notebook or whatever paper you're using to write down your answers. Okay, so the mass of the salt. Well, where was the salt? That's what was left in the dish after heating. And so good thing we took a measurement of the original dish, right? So if I take the 53.41 grams, that was the dish plus the salt. And so that was after heating. And we just subtract off the mass of the empty dish, 0.39. That's the dish. Then what's left is the salt. Okay, so we just subtract. And I'd be looking at about 1.02 grams. The salt would have just been the copper sulfate. Now, good practice when you get to these eventual free response questions that are more numerical and have more calculations. Obviously, we have to show all of our work. And it's not a bad idea to like circle your final answer, box your final answer, just so it's a little more easy for the readers to find what you mean to be your final answer. But we do have to show all our work. You can't just write the answers. All right, now sometimes people will say like, well, we could have just scraped the salt out of the dish and put it on the balance. I guess we could have, but how do we know that we got it all out? And so this is maybe just a little bit more precise way of getting the mass of the remaining salt after heating. Now the water lost, okay, so where was the water to begin with and where did the water go? Well, initially the water was in the hydrate. And then as I heated, the water was lost just to the air. It turned into water vapor. So if I take the mass of the original hydrate, 1.69 grams, and if I subtract the remaining salt, the difference was the water lost. So I know the salt now, that's the 1.02 grams of copper sulfate. Oh, so the difference is just the amount of water that evaporated. So I'd be looking at about 0.67 grams of water lost. So that the salt plus the water should add up to the original hydrate, the 1.69 grams. Okay, well that wasn't so bad, right? Now in 3 and 4, all we're going to do is turn these from grams into moles. Eventually I'm trying to find a ratio. I'm trying to find a ratio of like how many particles of water per how many units of copper sulfate. But when we're looking for a ratio of particles, we want a ratio of moles. Moles is a unit that measures particles. So I just got to take my 1.02 grams of copper sulfate, set up my little proportion to cancel grams and put it in moles. Then every 1 mole of copper sulfate would have the mass on my periodic table. So I just need to add copper, 63.55, plus a sulfur, 32.07, and 4 times the oxygen. And that'd be about 159.61 grams. Cool, huh? Okay, so now we divide, and I'm going to round to 3 sig figs. I'm going to round to my original measured numbers. The 159.61 is on a periodic table, and all periodic tables are a little different. I'm using the one with the AP packet, by the way. So I'm going to leave this as 0.00639 moles of copper sulfate. So here's where my sig fig rules come into play a little bit, because I know that those leading zeros are not significant. So then I go out to the 6, 3, and 9. Okay. So now we do the same thing with the water. I add 0.67 grams of water. And we just got to get it out of grams into moles. Cancel grams, we want moles. 1 mole of water. If I add 2 times hydrogen and 1 oxygen, 18.016. And now, note, that's really close to 18. If I were doing a multiple choice question and I somehow needed the mass of water, well, in a multiple choice question, you don't obviously have to show work. You're just picking the right answer. So when it's multiple choice, I round that all day long to 18. But when it's free response and I am showing my work, or like with these labs, when I'm showing my work, then don't round the molar mass. We'll round our final calculation, but don't round the molar masses. Leave whatever the periodic table says. And again, I'm using the one that's in the equation packet. So now I'm going to divide and leave 2 sig figs because my original measurement has 2. So it's going to be small again, 0.037 moles of water. Okay, cool. So I need to remember those 2 numbers. Now I've got the moles of salt, I've got the moles of water, and we want to find the whole number ratio. It's similar to finding like an empirical formula. It's just that when you're finding an empirical formula, you're looking for a mole ratio of the elements in the compound. Now I'm looking for the mole ratio of these 2 compounds. Okay, so that's number 5. I'm looking for this whole number mole ratio. And so just like any empirical formula, obviously these are not whole numbers. They're nowhere close to being whole numbers. So we're going to start by dividing them by the smallest. And we'll cross our fingers and we'll hope that fixes it. So I had 0.00639 moles of copper sulfate and 0.037 moles of water. Okay, I'm going to divide it by the smallest. So that would be the copper sulfate. 0.00639. And for sure I'm going to get a 1 here, right? Okay, so far so good. Now we divide this guy by the same. We cross our fingers and we hope and pray that this comes out to be a whole number. 0.037 by 0.00639. No, it's not quite. On my calculator I get like 5.79 and then blah, 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 a bunch of stuff. Bummer, it's not a whole number. Now, when we were finding empirical formulas, we said, okay, most of the time you'll probably get whole numbers at this point, and if not, maybe you get like a 0.5. And then to keep the integrity of the ratio, we could just multiply both by 2. Or if you got a 0.33333 repeating, you could multiply both by 3. Well, here's the problem. We've got lab data that's errored. I mean, the lab data could be flawed. So anytime you have a hydrate, it'll always be reported as 1 particle of salt per how many particles of water. There's always 1 salt and then X amount of water. Well, yeah, I didn't get a perfect whole number because obviously then my data has a little bit of error in it. So at this point in the game, with lab data, we're going to round. It feels kind of naughty, right? Like, no, I should find a multiplier. Yeah, but we're just going to round here, and I'm going to be close. Actually, the data's not awful. It's not going to be perfect because I must have made some kind of an error. So that I'm going to report my formula then as CuSO4 dot. I'm going to round that to 6. And this would be called my experimental formula. My experimental formula. Experimental formulas are flawed. Maybe, unless you got really good data. But there could be error in this one. Because now, for example, when I move on to 6, and it wants the percent water in my hydrate, well, now they say to use the theoretical formula. Oh, well, the theoretical means like the true formula. If you go ahead and you look under the conclusion, really, there's tons of different hydrates that you could choose for this lab, and here are just a few that are suggested, mostly because these all turn colors. Transition metals usually turn colors depending on their arrangement of ions or the charge of the ions. And so these hydrates are kind of cool to study in this lab because they always have one color when they're hydrated, and then they have another color when they are anhydrous. Then you kind of know like when to stop heating them. There are other salts that are like white before and they're white after. And so then they're kind of hard to use for this particular procedure because you just don't really know when to stop heating. But we could have used any of these. I picked the copper sulfate. Pentahydrate. So we're not awful. We're kind of close. So in number 6, they want me to refer to the true theoretical formula. So it should have been 5 waters. Okay, so the percent water in the hydrate is just mass of water. And so if I just make a little note, CuSO4 with 5 waters, that's the theoretical. That's what it should have been. Okay, so the amount of water, the total amount of water, 5 moles. So I'm just going to take my 18.016 times 5. And I'll say about 90.08 grams of water. So that's the total amount of water. That's this. That's the 5 waters. And then we just divide by the mass of the whole thing. So now I'm just going to take that 90.08 and add the mass of copper sulfate. And so now I'm just looking for like the mass of this whole thing. And remember that the dot does not mean multiply, right? The dot just means that the water molecules are loosely embedded amongst the copper sulfate units in the crystal structure. It just means that it's not that they're chemically joined together, that if I gently heat the hydrate, all I'm doing is evaporating the water and leaving behind the salt. It's a physical change. No chemical bonds are being broken. Okay, so my total mass of the whole thing should be about 249.69 grams. That's the copper sulfate plus the mass of the 5 waters. We'll divide, multiply by 100 to make it a percent. And now with a percentage like this, I don't have any measured data. I didn't measure any of this. It all came straight off the periodic table. So common practice then is to leave about 2 decimal spots in your percentage. So I'm going to leave this as 36.08% water. If you leave 2 or 3 decimal spots, that's plenty. Awesome. Okay, number 7, we're cruising. Write the complete name of the hydrate chosen using the theoretical. So the name should be copper sulfate. And because it's a transition metal, I do need a Roman numeral in there. Okay, so we think about the charge on sulfate. And for a while, you might find yourself not only having the periodic table handy, but also that list of polyatomics that are in the Chapter 2 lecture guide. You can use that, and I'll link it in any assessment where I think you might need it. Sulfate, SO4. This group is -2. And since there's only one copper, the copper must be +2. Oh yeah, copper 2 sulfate. Copper, Roman numeral 2, sulfate. 5 waters would be penta hydrate. Pentahydrate. There's the name of the hydrate chosen. Fantastic. All right, we're almost there. 8 and 9, I like these. 8, why would it be important to mass the anhydrous salts somewhat soon after cooling? And I think we mentioned this a little bit in the lab, in that, I mean, obviously you don't want to take something right off an open flame and throw it on the electronic balance. It's just not good for the pan of the electronic balance. So we let the hydrate cool for just a little bit, but it's not like I would want to let it cool for an hour and then come back and mass it. Hydrates like water. I mean, they're stable when they have water in their structure. And there's water in the air. So if you wait too long, the salt, the anhydrous salt, could absorb water vapor from the air. We don't want that to happen. I mean, not if we're trying to get an accurate mass. So So that could be a source of error if you waited too long, which I don't think we did. But it could be an error. Now, I did try to overheat one of the hydrates in the lab. I wanted to try to, I don't know, scorch it a little bit. What could happen if the hydrate is overheated? Well, probably two things. One, I didn't really see, but I could say the hydrate, like that solid that's in the dish, it could splatter out of the dish. So sometimes, like, you'll see a little residue, like on the lab table, like there's little blue speckles on the table. Uh-oh, we overheated. Snap, crackle, pop, it jumps out of the evaporating dish. We don't want that to happen. Then it's going to seem as though I lost way too much mass. We're assuming that the mass lost should just be the water, but now you might have some of the hydrate or some of the salt laying on your table. The other possible issue could be decomposing the salt. Now you could start to drive off some of the oxygen from the sulfate. We don't want to do that either. This really should be a physical change where we're just separating particles, but we're not breaking any chemical bonds. Aha. But if I heat too strongly, then I could start to decompose the salt. All right, so here's my analysis, and all you have to do is write these on a separate sheet of paper, and then eventually you'll upload a photo of your work. So we've got the data, we've got the analysis, and finally the conclusion. To be honest with you, the conclusion is probably the part where I'm going to spend most of my time when I look at what you submit to me. The conclusion is a paragraph. When you write the conclusion, you'll kind of go back and look at your data, compare your theoretical formula to your experimental formula. And then some of the most important parts of the conclusion are your explanation of error. And we want these to be logical errors. Was my data too high? Was my data too low? I'm not just going to go and think of any possible error under the sun. It needs to make sense in explaining how my experimental formula compares to the theoretical. And we're also not going to say things like, I don't think I did the calculations right. That is not a laboratory error. Then do the calculation correctly. Like, why would you submit work if you know your calculations are wrong? Like, that's a you problem. Fix it before you turn it in, right? So doing the calculations wrong is not a source of laboratory error. Other things that would not be acceptable sources of laboratory error. Well, okay, let's just say you put this down. I think I measured wrong. Okay, now that could be a possible error. But then what measurement is wrong and what do you think went wrong? So it could be that, I think I made a mistake with one of my masses and that I forgot to zero out the mass of the evaporating dish. Or it could be, I think my mass is wrong because I remember there being some compound that kind of spilled on the electronic balance pan. The pan wasn't clean, so I think my mass might have been too high. Okay, now we're talking. Or I think my sample might be contaminated, and I saw that I used a dirty beaker, and so that's why I think my mass is too high. That's okay, but you can't just go on a blanket statement like, I think we screwed up the mass. I think we measured wrong. What measurement is wrong and why is it wrong? We also don't want to say like, my lab partner screwed up. Okay, that could be true, but then what did they do wrong? Explain the error. Kind of along the same lines. Don't put like, I don't think we read the directions. Well, as long as we're virtual, that's not a you problem. That would be a me problem, right? I'm hoping that I read the directions correctly, but that's not a laboratory error. Like, do it right then. Or if you didn't read the directions correctly, then what did you do wrong? Oh, we used 10 grams, but it was supposed to be 1.0. Okay, now we're talking. Now, in this particular conclusion, we're supposed to have an answer of copper sulfate pentahydrate. So if you got that, great. I mean, then you would say something about, yeah, you know, we made sure that we heated gently, we did this and this, like these are the things that we did in the lab to ensure that we got good data. Now, if you didn't get 5 waters, maybe you're kind of like us and we got too much. So ours was like copper sulfate hexahydrate. Okay, so it looked as though we had too much water. That's impossible. And the real structure of this solid is that there are 5 waters embedded amongst the copper sulfate. It's really 5. And so it's impossible to have too much water. So we have to think, like, why does it seem as though we have too much water in our hydrate? Well, the water is the change in mass before and after heating. And so it looks as though the mass changed by too much. It looks as though there's too much water, but obviously that's impossible. But really we just had too much change in mass. We could say the change in mass is too high. Now that change in mass is supposed to be just the water. I must have lost something more than water. And so I didn't really notice a lot of splattering, but it could be that I overheated slightly. And to remedy that, we want to make sure that everything is in a nice even layer on the bottom. I don't have any big chunks, or I kind of like shake the dish a little bit so that the salad heats evenly. Maybe I should have paid more attention to that, so that the outside of the sample heats evenly compared to the inside. Maybe the outside was starting to overheat just a little bit. But there's more to the change in mass than just water. And so again, that could either be the splattering, or it could be that maybe we overheated just a tad bit. Now the other option, which is good to understand both, because now you could get a free response question that's kind of labby in nature. And so we want to understand all sources of logical error. What happens if the data is too high? What happens if the data is too low? So what if somebody had like copper sulfate and they only had like 4 waters? Okay, well now their change in mass is too low. Change in mass is too low. And they were supposed to get more water out, and they just didn't heat it long enough. Okay, so obviously then they would say, yeah, that's my source of error, is that I should have heated it a little bit longer to see if I got the 5 waters off. If I would have like taken the mass, then heated it again for just a little bit, if I would have noticed that the mass went down again, then I know that my first mass did not have all the water out. So maybe we should have done something like that. Maybe we should have heated it for a small amount of time, taken the mass. Then heated it for another small amount of time, take the mass again. And then see, like, okay, if the mass keeps going down, then I know that I'm still evaporating water. When I get to a point where I get 2 masses that are the same, then we should be at a point where we call it heating to constant mass. And then I should have the 5 waters off. So that would just be underheating. Awesome. So you're going to write a little paragraph, and then all you got to do is upload photos of your work.